And if the Raptor 1 was a modular desktop computer with exposed cables, and the Raptor 2 was a refined laptop with a dedicated motherboard, the Raptor 3 represents the jump to a system on a chip. In modern computing, the system on a chip seen in the likes of Apple's M series or high-end Snapdragon processors integrates the CPU, GPU, neural engine, and memory into a single silicon die. This integration eliminates the latency of external buses, reduces power consumption, and drastically shrinks the physical footprint. And in the Raptor 3, SpaceX has achieved the aerospace equivalent of this architectural feat. The engine no longer appears to be a collection of discrete components bolted together. Instead, it has become a monolithic solid-state propulsion unit. The external plumbing, which previously defined the silhouette of the world's most advanced engines, has been folded into the internal geometry of the hardware. This is not merely an aesthetic choice. It is the ultimate expression of hardware encapsulation, a design paradigm where complexity is managed through total integration rather than external organization. In the philosophy of hardware encapsulation. In software engineering, encapsulation is the practice of bundling data and the methods that operate on that data into a single unit, hiding the internal state from the outside world. This prevents external actors from interfering with the internal logic and simplifies the interface. Raptor 3 applies this principle to high-pressure fluid dynamics. And by moving the fluid paths, the veins of the engine, inside the structural walls of the combustion chamber and turbopump housings, SpaceX has created a protective shell for the engine's most critical functions. In previous iterations, a stray piece of debris or a localized thermal spike could sever an external sensor line or a thin-walled bypass tube, leading to a catastrophic system crash. In Raptor 3, the code of the engine, which is the flow of methane and oxygen, is protected by the hardware, meaning the thickened, load-bearing walls of the engine itself. And this shift represents a move away from the maintenance-heavy era of aerospace. When every component is exposed, every component must be inspected, shielded, and replaced. When those components are integrated into the primary structure, they inherit the robustness of the structure itself. The engine ceases to be a machine that requires a delicate environment and becomes a ruggedized appliance designed for the vacuum of space and the searing heat of planetary entry. And direct metal laser sintering as the compiler. To achieve this level of integration, SpaceX leaned heavily into the manufacturing techniques discussed in Chapter 5.4. Traditional casting and machining are incapable of producing the internal topologies required for Raptor 3. You cannot drill a curved, variable diameter cooling channel through a solid block of Inconel with traditional tools. And instead, SpaceX utilizes advanced direct metal laser sintering. If we continue the computing analogy, direct metal laser sintering is the compiler that translates the digital CAD model into physical reality, layer by 50-micron layer. This allows for the creation of conformal fluid galleries, which are internal passages that wrap around the combustion chamber or the turbine inlets in mathematically optimized shapes that minimize pressure drop and maximize heat transfer. And these internal galleries replace what used to be external flexible hoses and hard lines. In the Raptor 2, a manifold might have 3 or 4 external outlets leading to various cooling jackets. In the Raptor 3, those outlets are internal vias, much like the microscopic vertical interconnect access points in a multi-layer printed circuit board. The propellant moves from the high-pressure pump directly into the walls of the chamber through a labyrinth of 3D-printed channels that are invisible to the naked eye. This eliminates dozens of potential leak points, the flanges and seals that are the bane of high-pressure rocket engines, and the elimination of the fire suppression overhead. One of the most striking visual differences in a Raptor 3-equipped Starship is the absence of a complex fire suppression system within the engine bay. In earlier versions of the vehicle, the spaghetti of the Raptor 1 and 2 necessitated a massive network of methane and oxygen detectors, along with nitrogen purge lines to snuff out small leaks before they could become infernos. And every external joint is a potential leak path. In a full-flow staged combustion cycle, where gases are heated to extreme temperatures and pressurized to over 300 bar, even a microscopic pinhole leak can act like a plasma cutter, slicing through adjacent wiring or plumbing. To mitigate this technical debt, SpaceX had to add defensive code in the form of heavy shielding and fire suppression hardware. And Raptor 3 deletes this requirement. By moving the plumbing inside the primary metal structures, the leak's surface area is reduced by nearly 90%. If a leak does occur within an internal gallery, it is contained within the structural wall of the engine. This intrinsic safety allowed SpaceX to strip away the heavy nitrogen tanks and plumbing used for engine bay fire suppression. The result is a massive reduction in dry mass, which translates directly into increased payload capacity, the ultimate metric of any launch system. And thermal resilience and the re-entry profile. The SoC design of the Raptor 3 is not just about launch. It is arguably more about the return trip. As established in our introduction, the goal of the Starship program is rapid and complete reusability. This requires the engines to survive the brutal environment of atmospheric re-entry, where the base of the ship is blasted by a plasma wake of compressed air. And in the Raptor 1 and 2, the external components, the actuators, the sensors, the small diameter lines were highly vulnerable to this heat. SpaceX had to develop complex engine blankets and deployable heat shields to protect the delicate parts of the engine. These shields were themselves a point of failure. If a blanket tore or a shield failed to deploy, the engine would be bricked by the thermal load. And the Raptor 3 is designed to be its own heat shield. Because the exterior is essentially a smooth, monolithic surface of high-strength alloy, there are no catch points for the plasma. The engine can be exposed directly to the re-entry environment with minimal additional protection. The high-mass components, the turbopumps and the main combustion chamber, act as a heat sink, while the internal propellant channels can be used for regenerative cooling even during the descent phase. And this is the hardware equivalent of hardened code. By reducing the surface area to volume ratio of the engine's critical components, SpaceX has created a propulsion system that can withstand hundreds of thermal cycles without the need for the extensive refurbishment that plagued the Space Shuttle's RS-25 engines. And digital control and the software-defined engine. While the physical structure of the Raptor 3 has become more analog and monolithic, its control system has become more digital. The integration of the system on a chip extends to the electronics. In previous versions, the engine control unit was a separate box mounted to the side of the engine, connected by a thick wiring harness, which was the aforementioned trunk of the Raptor 2. And in Raptor 3, the sensors and actuators are increasingly integrated into the chassis of the engine. The move toward high-torque, direct-drive electric actuators has eliminated the need for complex hydraulic or pneumatic lines. These actuators are controlled via a simplified, high-speed data bus. And this allows for a software-defined engine architecture. Because the internal fluid dynamics are so precisely controlled by the 3D printed geometry, the engine control unit can use sophisticated observers' mathematical models running in real time to infer the state of the engine from a much smaller number of physical sensors. If the Raptor 1 was over-instrumented, meaning it had too many print statements, the Raptor 3 uses telemetry compression. It monitors a few key high-fidelity nodes and uses the underlying physics models to ensure the system is operating within its nominal envelope. And this reduction in electronic complexity further enhances reliability. In the high-vibration environment of a rocket launch, every connector is a failure point. By integrating the sensors and reducing the wire count, SpaceX has hard-wired the reliability into the system. And redefining the unit of power, the transition to the Raptor 3 architecture fundamentally changes how we think about rocket engines. For the last 70 years, a rocket engine was viewed as a collection of parts that required constant tuning and maintenance. It was a subsystem of the rocket. And the Raptor 3 turns the engine into a commodity unit. It is a black box of thrust. You bolt it to the thrust puck, plug in the primary propellant feed lines and a single data or power umbilical, and it works. This plug-and-play capability is essential for the Star Factory production model. When you are building a ship every few days, you cannot spend weeks integrating an engine. You need an engine that is pre-integrated. And this system-on-a-chip approach also simplifies the Starship system architecture. Because the engines are so self-contained and robust, the ship's design can be simplified. There is no need for complex thermal protection systems around the engine bay, no need for extensive purge plumbing, and no need for the massive umbilical plates that characterized previous generations of rockets. And the aesthetic of efficiency, there is an undeniable futuristic art quality to the Raptor 3. Stripped of its guts, the engine looks more like a sculpture than a piece of industrial machinery. This is the visual manifestation of the law of deletion. When you remove everything that is not essential, what remains is the pure expression of the engine's purpose. In the smooth, matte finish of the 3D printed superalloys, the absence of bolts and flanges, and the streamlined profile all point toward a design that has reached its theoretical limit. In the world of high-performance engineering, there is a saying, if it looks right, it flies right. The Raptor number 3 looks like the pinnacle of the FFSC cycle because it is. Every gram of metal is doing double duty, providing structural integrity, while simultaneously acting as a conduit for the most energetic chemical reactions humans have ever controlled. And this internalized complexity is the hallmark of a mature technology. Just as we no longer think about the billions of transistors firing inside our smartphones, future Mars colonists will likely view the Raptor number 3 not as a complex machine, but as a reliable, solid-state utility that provides the bridge between worlds. And hardware encapsulation as a competitive moat from a strategic perspective. The Raptor 3 integrated design represents a significant moat for SpaceX. While other aerospace companies are still struggling to master the breadboard phase of FFSC engines, SpaceX has moved 2 generations ahead into system-on-a-chip hardware. And the difficulty of designing and manufacturing a Raptor number 3 cannot be overstated. It requires a full-stack integration of computational fluid dynamics, material science, 3D printing software, and flight data. You cannot copy a Raptor number 3 by looking at it. The logic of the engine is hidden inside its walls. To reverse engineer it, one would have to slice it into thousands of cross-sections and painstakingly map the internal galleries, and even then, without the specific compiler settings used during the DMLS process, reproducing it would be nearly impossible. And the Raptor 3 is the ultimate realization of the first principles approach. It is the end state of a decade of relentless iteration. It is the engine that takes the technical debt of the last century of rocketry and pays it off in full, leaving behind a streamlined, integrated, and incredibly powerful machine that is ready to make life multiplanetary. And as we look toward the final metrics of this evolution, we can see how this radical integration manifests in the hard data. The system-on-a-chip design isn't just about looking sleek. It's about the brutal optimization of the thrust-to-weight ratio and the total minimization of the part count. And the physical transformation from the spaghetti of the V1 to the monolith of the V3 is best understood through the lens of cold, hard numbers. To truly appreciate the scale of this engineering achievement, we must look at the performance deltas across all 3 generations. This brings us to the final analytical breakdown of the Raptor's journey. 7.4 feature comparison, weight, thrust, and part count.